Okay. So today we are getting into the first actual exploit of the class. A little exciting. But today's topic is on buffer overflows, if you remember from the bug last lecture, and general stack exploits, right? Everything we do in the first half of the class is purely stack-based. There's separate exploits dealing with heap, which is, I think, after spring break with the timing. But we gotta start somewhere. So just real quick, topics to cover. Project 1 is due next Tuesday at midnight, and we're going to be giving out a second homework today too, also due Tuesday midnight. Any questions with the project so far? Yeah.
How long do you want to write up the last question today?
We'll send an example today. You want to get on that? We can maybe do the final. You can release?
Yeah. Oh,
yeah. So we cut the final from last year. So we can just show the final write-ups, like with the names blurred out, and we'll pick the good ones. Usually there are a few pages, right? With all your screenshots and everything, it comes a few pages. It's not like, it should not take you 5 hours. It should take you maybe 1. I recommend documenting while you do the last challenge for it, and it'll speed things up a lot. Oh, someone pointed out challenge 3 has a bug where if you get like an unlucky value for one of your parts of the password, it'll like infinite loop. So just like, if you think it should be working, run it twice just to check. Maybe 3 times. And we'll take that into account for grading, so don't worry about it. I'm too lazy to patch it. I think it'll take too long. Any other questions? No? Yeah.
Also, have the homework due Thursday instead of Tuesday, so we don't have 2 due dates on.
I will consider it. I think this homework is lighter than the last, right? Yeah. This homework is like, write a sentence explaining what something does, and not, here's 4 functions to program in some way.
We can do Thursday though.
Yeah, we can probably do Thursday. Because I don't think we have homework 3 coming out for a while. Yeah. Any other questions?
So you'll post something on Check this one.
Yeah, I'll verify.
So that it's clear exactly.
Yeah. Anything else? We all set. Any questions from last lecture? No? So just a quick recap of the class so far. So the first week was CS230 review. We learned some assembly. We did DLF file structures. We started working with Ghidra, GDB, Pwn tools, all that stuff. And last lecture we did code auditing, right? So we looked at possible C bugs that could, screw you over in case of someone trying to break your program. Something that I want to show you real quick. If my VM wants to work. Okay. So we mentioned that a lot of these bugs are like very simple to do, human error. So I have a quick program called segfault that has one of those bugs. I just want to show. The compiler will actually warn you about these bugs a lot, right? So here it actually tells me, if it's a little small, that I'm using gets and that it's a bad function to use in practice. So there are some checks for this when you're writing programs. Usually if you're working at a company with a 1,000,000-line project, it's not your problem to deal with these bugs, and people don't, so they add up over time. Again, Rust tries to fix all of this, but then your compilation times grow drastically. And if it takes 10 minutes to compile or an hour to compile your work, that's dollars spent, so people generally don't do it. And then there's also the overhead cost of teaching your programmers Rust. I bet you only a few people here actually know how to use it, so it adds up over time. But okay, let's go. So just to recap, so with all these bugs yesterday, I think they were all stack-based, right? Except maybe we did like
a few were
double free, right? So all these bugs that we looked at are generally ways to corrupt stack memory. And when I say stack memory, these are the function stacks that we've been talking about for a while. And we didn't really look at any interesting things we could do. Some of the things we talked about is you can corrupt local variables. Maybe you can corrupt a return address, but generally these just lead to crashes, right? So if I go back to this program, the segfault program where the code's here, you can see I just use gets. And if I run the program and just give it some input, nothing happens like it should. I don't have a print or anything. But if I give it a lot of input, I get a segmentation fault and it crashes. You may have seen this in 230. Nothing really is interesting here for us as an attacker currently with this payload, but we do get the program to crash, right? And if we go to statistics, in 2021, most of the exploits that were found, or not most, but 15% roughly, were denial of service attacks, which for us, if we're running a program on our laptop to maybe automate something, it's not a problem. But if we're a company and we're running, say, an Apache web server, if someone can just send a 8-byte, 10-byte payload to our website and crash the entire thing, that's a big implication for the company. Any questions on this? Okay. So we looked at this last class, but here is a classification of exploits. And if we go to overflows, which is the one that we're doing, it might be a little small, but you can see it's almost 12% of all exploits in the wild are this technique that we're learning today in class. And then stemming from that, this number is for the denial of service attacks. That's another 24% on top of that. So roughly a third of all bugs are denial of service and buffer overflow related. So big implications. And as we'll see, buffer overflows can also lead to code execution, not just denial of service. So very important. So let's get hacking. So this is our program for today, our starting program for the lectures. On the right, we have a little demo of the stack. This main program just takes in the buffer with gets and then prints it out, right? But the thing that prints it isn't the buffer, it's the integer above it, the long, right? Who sees the issue with this? Yeah.
It's gets, not get n or whatever it is.
Yeah, right. So we use gets, obviously a problem. If we compile this program with GCC, it will yell at us, and that's one quick way to verify. Something people do often is if you're reverse engineering a big program and you can isolate a function, people will just compile it and see the compiler says there's an error in it. There's a lot of automated tools that try to do things like that just take the decompilation and then parses it, see if there's bad functions or if there's bad function calls with printf. Because printf isn't inherently bad, but it'll look at the arguments and see if you have it called in a bad way. So that's something tooling does, or you can check manually. So the idea of this program that we're looking at in class is we can overflow the buffer with gets, right? That's not very interesting. Let's try to change the value of overflow me from 0, right? That's what we're going to try to attempt to do. And you can imagine that maybe instead of just some random long in the code, this would be a check variable, right? To see if your input is valid. Or maybe it's a password hash that you're verifying against, and if you can change the password hash to anything, you can authenticate as a different user. There's a lot of interesting things that random variables on the stack can be. So let's walk through it a little bit. So first thing that happens in the function is called, you set up the stack frame with the return address and the base pointer from the previous function, right? So it should be familiar. And then we're going to initialize local variables, okay? So roughly in the code, we're about here. We're going to call our gets now. And this is typically what it looks like, right? We can give it some trash data. This is 32 bytes of random data. Nothing to see. That's too interesting. And then we're going to print, and it'll print 0. If we run it, it should be fine. But now let's consider the case where we give it more data, okay? The issue here, can anyone tell me what it is? Yeah.
You can use gets, then give it too much data, which will overwrite overflow me variable.
Mm-hmm.
So you can kind of just change what overflow me is.
Yeah. So that's the main idea. If we were to actually run this program in the terminal, you would get whatever FFFF turns into as a long, right? Later in class today, we're actually going to be walking through a few examples. This class will be mostly in the terminal. But this is the theory of buffer overflow, right? You just try to continue writing data until you hit local variables or whatever you want to hit. Something to note though is that this only goes one way. This only goes up. Okay, so if the local variable was instead, so let's go here. I wrote pretty much the exact same stack where the buffer's on the bottom, our integers on the top. Right, gets always writes up because we do positive indexing and that's the higher values on the stack. Right, so an actual defense mechanism that is used in real programs and pretty much everything you compile now is that I'll always put buffers on the top in case there's an overflow. So if I compile this with the normal flags and I don't do anything special to make it break, then our integer variable will be here and our buffer will be here. And even though it's kind of based on how we declare the variables, the compiler will do that for us, right? Yeah.
Can you still like overflow the buffer and then like change the return address?
We talk about that later. Don't get ahead. Yeah.
So does it not segfault when we put in like more than the space of the buffer
No.
with gets?
So the reason we get segfaults, right? Segfaults stand for when the program crashes unexpectedly. And if we change that local variable, the program will continue to run, exit the function, and nothing with exiting the function changes, right? So it'll still exit main the usual way. All that happens is that it won't print 0, and nothing outside of that context has changed. So the program runs like it usually does, which is very important when you're trying to do an exploit versus just a denial of service, right? Because if we want to like write an exploit that actually continues and does code that we want to do, we can't have the program crash, right? It needs to exit gracefully. That, or it needs to continue running and we have it do something for us forever, right? A lot of, if you see like Bitcoin miner malware, right? What it'll do is it just lives in the program that's already running on your computer, and then it'll spawn a thread to continue running gracefully, and then it'll return to the code of the original program. And then that separate thread will just be Bitcoin mining, right? So you get things like that. Yeah,
So is the goal to like overwrite the return objects?
later.
Oh.
Right now, we're just seeing what we can do with local variables.
This might be a question from an earlier lecture, but why doesn't the stack just dynamically reallocate itself bigger to hold more data?
That's exactly what the heap's for. So the stack is for local variables, right? And all local variables we declare at the start of our function. Like if you're running code, local variables we have to declare. Just like how we have to declare global variables and those get loaded in somewhere else. That's exactly like if we run malloc, right? Malloc allocates on the heap, and that's how we can do dynamic stuff. And then you keep the pointer to the dynamic data on a stack. So that's how you do it. Yeah.
So you have, earlier in one of the things you showed, you had your 32 bytes of the buffer you're overflowing,
Mhm.
and there's 8 bytes in between your data and then the overflowing variable. What are those? Is that just a pointer?
Computers like to optimize in weird ways. Sometimes they'll put random data between variables. It usually always tries to allocate in chunks of 8 because of just how pointer arithmetic works. If you have extra space between variables, sometimes, depending on the compiler, like this is all compiler specific, mind you, but it'll do extra data between your buffer and other things in case you have like off by 1 errors with your null bytes for strings. So some compilers just do that as a safety check. Anything else? Right. So again, compiler specific, an easy data protection is just to put the buffer first, right? And that'll protect us from overwriting local variables. But then you have to ask, what if you have multiple buffers? And what if multiple buffers are broken? Okay, so like it's not that great of a fix, but it's an easy one. Any other questions, please? Okay, so something that we can do is we can overwrite overflow me, like we said. Perfectly a huge problem. This in itself can lead to a lot of bypass checks. There's been bugs in, okay, who knows the command sudo? You probably had to use it for this class, right? Sudo gives you elevated privileges, makes you basically administrator on Linux. Sudo had a 1 byte overflow and it completely got you full administrative privileges, right? Is it full
I think it was more than they had a bigger overflow bit.
sudo edit? I thought it was a 1 byte. What's the exploit that's like a 1 byte overflow that's full?
It wasn't in like a real target that where we demonstrated it's like null byte poisoning or something.
Okay.
Like we showcased it last year, but the sudo exploit they were able to get a bigger overwrite.
But generally, like even 1 byte, there's been historical cases where 1 byte overflows can really screw you. And like you don't even need to use gets for that. That can be fgets where you just count wrong. Okay, so you have to keep that in mind. So what if we wanted to give it even more input, right? So like people were hinting to, we can completely override the base pointer and return address, right? Which doesn't do anything in our current functions, like context, right? The current function doesn't rely on that information at all. So in this case, main wouldn't break from overriding that data, but once we return from main, that's when issues happen, and that's when things like site faults happen, right? And the main reason you probably see the send fault in this program is because we're overriding the return pointer with just A's, and that probably leads to like invalid code. So the reason we're send faulting here is we're probably accessing memory that's not executable, and the operating system's yelling at us, right? So if we actually put like the address of valid code from our program, then it wouldn't send fault. It would keep running until it runs into another issue with probably like butterfly effect. If the stack isn't set up from overriding base pointer, there'll be an issue. But let's just think of the easy theory now. We can override base pointer and return address. So anyone have implications of that? Not from the exploit, just from a site fault standpoint.
So if you had like code that you wanted to run, would you overwrite to the address of the code that you wanted to run?
Yeah. So say we had code somewhere that we wanted to execute, whether it's like in the program or something. We could change the return address to the address of that new code. Something we have to keep in mind though is that by changing the base pointer, when we eventually call that new function, it'll use that base pointer as its stack. So we have to make sure we also change the stack to valid memory locations. So usually that only matters if you're jumping in the middle of a function because every function sets up its stack at the start. So say, for instance, right, we have main, which is like exploitable, right? And we have that buffer overflow, and we can return to any other function. So let's say we have off check, right? Some function that does some authentication check. We can find ways to pass it the right parameters and everything, but we're not admin. So we want to bypass part of this function, right? If there's like an if statement where if admin unlock, and then like else do nothing, right? So something that we can do is instead of actually jumping to the start of this function by overriding a return address, we can actually jump into the if statement, right? And suddenly we don't even need the admin password. We can bypass any checks. And this is all from a gets overflow for, maybe the main function was taking the username of the user you wanted to log into. And if you give it a bad username, you can just bypass all off checks. This is actually something that happens a lot. I bet you, if some of you look at your 230 projects, something like this exists in it, right? I would go back and compile all your 230 projects and see if GCC yells at you. Okay, so that's a little bit of the theory. We crash the program, and then we have to consider, we can change all local variables. Base pointer is important because before, this is a bad example because we're doing main, but say we are already in some nest of functions. If we want to return to an old function that's already called and return to the context of the previous stack variables, we can restore that by using the right base pointer, and then return that just for any code. Yeah.
So how overwriting the local variables help us?
So say because of, you're having trouble. Also keep in mind that a lot of what we're saying is ideal context. A lot of programs you'll have, maybe the buffer can only be ASCII characters because to do is like check to see if it's valid letters for a username. Or maybe like you can't write null bytes because the input functions are using will stop taking input upon a null byte, right? So a lot of these times you can't just say jump into the if statement. you can't just like do whatever you want. So you have to work with constraints, and sometimes changing local variables allows you to work with those constraints more. Like instead of just jumping into the if statement, maybe we overwrite the local variable that is the hash we're checking against instead, and that would be more flexible. Anything else? Right? Okay. What is my next slide? No. So let's do a little demo. If everyone installed the basic overflow, I can pull it up on screen if you didn't. But this is exactly the code we're just going to show. So we're going to run it in GDB. We're going to see it live with GDB. Something that you will need to get used to for this class is it's one thing to know the theory, but it's another thing to actually have the practical skills to do it. Okay. So let's run GDB on the program. And we'll just break into main and run it for you guys. Okay. So we can see we're in main. You can see the gets call and the disassembly. Here's the entire stack. So this is the part that we need to keep attention to. So if I just continue the program and do the input, or actually, let me rerun it and then break after the gets call. So I'm just going to set a breakpoint right after the gets call. You can look at the disassembly to do this. So gets is at main plus 32. If you do plus 37, it'll break right after the gets call if you continue and give it input. So that's what we're just going to do. And I'll just give it 8 A's. So because we called gets, and gets is, like we said in our program, the buffer should be on the bottom because I compiled it without stack protections if you use it the source code. The bottom 4 bytes, GDB does it upside down, which is a little annoying, but you can see the bottom 4 bytes, the data in it is an A, and if I do, I think the command is examine string RSP. Yeah, you can see starting at RSP, if we look at that as a string variable, we see all the A's are there, right? And if I rerun the program, continue to give it input, and I just do A a little bit more, that's probably not 32. And we can see it's still fine. What we can see here is the base pointer, right? So if we consider how much space we took up, I probably roughly took up up to here of A's, and there's still more space between our integer and the base pointer, the return address and stuff. So still perfectly safe. But now, what if I run it one more time, continue to give it input, and I give it, Amen, you said there was an extra 8, right? 2, 3, 4, 5, 6. I think that's enough? Okay. So now, if we continue the program, I gave it, I want to say 40 bytes. I might have clicked one more time by accident. It should print the integer like the source code says, right? But suddenly, it's no longer 0, right? The buffer is 32 bytes. I gave it 40. And this is a really weird number that it's printing. What we can do, though, is, let me open Python real quick. And I'll just quickly convert it into hexadecimal, and we see 0x411414, which is just A's, right? That's the value of A's, 0x41. So suddenly, by just giving a bunch of A's, we've completely changed the value that it's printing. And this is generally a problem because usually you don't just print values like this, you do checks. You can even do things like if you have a for loop, you can change the value of the iterator and skip certain values for for loops. All different types of things. You can also change pointers to point to different things in memory, whether that be code, different data, null bytes, so it doesn't check any data. Any questions? Okay, and then just for a quick demo, we're going to talk about this in depth more. If I continue it, we're going to give it, oh, that's not the A's. I'm going to run it We'll continue to give it input. 8. How many bytes do I need to give it? 32. All right, and then we'll check on some B's and C's, and then see if I did this right. Oh, I should have done one more. But we can see RVP now points to a bunch of C's. If we actually go to the view of the registers, RVP is now the actual value that RVP is pointing at is corrupted with C's. So let me see if we actually exit main, will the base pointer be screwed up? Symbol main. So we go to the end of main. We see the RVP still pointing to a bunch of C's. We're going to step through this leave opcode, which basically just cleans up the stack. It like pops RVP, subtracts the RSP back to where it should be. And we go to the register. RVP is now corrupted, right? So the function that initially called main will now have all its stack data and local variables completely incorrect, right? This could lead to issues like also indexing code or memory it shouldn't have access to, which could cause a site fault because of how paging works. Maybe the operating system doesn't think the program needs that page of memory. If you're a 377 kid, you won't understand. But we'll have a scope for class. Any questions? Yeah.
You could use this to put some address for like RVP that.
Mm-hmm. So a big thing to note here is we didn't change the reference for the stack for our current function. We changed the reference of the stack for the next function, right? So no matter how much like overflowing we do, the RVP and RSP for our current function is the same. But if we return, that can maybe be useful. In practice, it's not used as much, but it's something you'd be aware of. Like if you get into like advanced exploit development, where like, okay, the government or some like independent bug hunter is paying you to find bugs in the Linux kernel. This is stuff you might have to worry about. But generally for this class, you only really care about corrupting the instruction pointer, and we'll only be jumping to starter functions because it's very rare that you have that many limitations, but it does happen. Any other questions? Okay. So now we're going to be looking at a pretty important topic with buffer overflows. This is our new program. Basically the same thing. We get a buffer, right? There's no local variables now, and we return 0 and do nothing. The goal of this program, which is roughly what you're doing in the new project, or project 2, I should say, project 1, is we need to call this win function, but how, right? There's no direct call in the code. If the compiler was smart enough, it would just delete the function, but we're not that cruel. But you need to print you win somehow without the code doing it itself, okay? And you can think in real life, right? Something would eventually call win. It's not a problem. But indirect calls are really important in exploit development. Okay, like the code that you find a bug in could be like stuff that we've worked on in the past. Will be like a logging function that just prints messages and logs from different parts of the entire system in like a camera maybe. And maybe you want to access the actual pins that read and write from the camera. But that's completely different functions, right? And there's no way the logging function is going to be calling reads to the camera directly, right? It's probably everything's going to call the log function and just send it data. So you need to find ways to indirectly call things in exploit development. This is one of the ways. So how can we do this? Yeah.
Get the address of the win, like the start of the win function, and then overflow the buffer and then put that address as the end, like specifically overflow that amount.
Exactly, right? So what we want to do is find the address of win in the file, override the entire buffer, the entire stack, base pointer, return address, and then to jump to the win function, we want to set the return address to the address of the win function, right? And then when main is done and it returns, it will still return 0 as its like return parameter, right? That's set to the RAX register as like, 0 in this instance is like a success. But if we were giving back a variable for some data, it would be in that instance. But instead of returning 0 to, the start function which calls main, we're going to be returning 0 to this one function now, right? So we completely can change the function that we're going to return to. So again, note that everything we're learning right now is just working because there's no mitigations, right? In this instance, the change of orders of variables, if we had that mitigation, does nothing to stop us from returning to different functions. But there are mitigations that we learn in the later of the class that completely stop buffer overflows like this, right? And then also, you have to think about how the hell do we learn the address of win, right? Nowhere in the code are we shown that when it compiles to. And if we're an attacker from the outside, nowhere in a normal program do we get addresses of functions in memory, okay? So you need to consider how to get that. And the project we're doing currently, it's not an issue because what we can do is we can just load it in GDB, right? So if I just run disassemble main, right, I can just see this is the address for the first opcode. And we can put that in our payload. Okay. What else do I have on these slides? Right, so this is basically the idea that we're going to be doing. We fill the stack with complete junk until we reach the base pointer. We can also, in this instance, overwrite the base pointer with whatever we want. We don't really care. And then we'll set the return address to the address of win, and then we will run the program and hope it works. Okay. Yeah.
Because of like address virtualization, if you want to jump to code in another process, would that basically be possible?
We talk about virtualization in a bit. So something that we'll talk more on later is programs can be not static or dynamic. What's it called? I wanted like a word for reload. Or what? Relocation. AOSOR. Okay. So functions can either, by default, right, there's this thing called ASLR, right? But without ASLR, programs are always loaded in the same place in memory every time, in terms of virtualization, right? Let me see if this is actually, okay, keep track, this is ASLR.
As a very quick TLDR, no, you cannot jump into other programs from your program.
Okay, so programs can be loaded in virtualization two separate ways. One is that they always use the same address, right? And this is really convenient because you can hard code addresses in your code. If I want to jump to main, I can always say have main start at 0x40, and we will always jump there, and it just puts a constant in the code. Or the standard now, which is better for protection, is we do everything relative. So in my program, let's say main is now, instead of always being at byte 40, is now offset 40 bytes from the start of my program. And then function 1 will be offset 100 bytes from the start of my program. And then the program only needs the operating system to tell them where it starts to be loaded in memory, right? So that means if we're writing the exploit, instead of it always being in the same spot, and we can just do that on any system that it's loaded at this address, we now have to leak the start of the program and then do everything offset from that. And getting that leak is hard.
Okay.
Yeah.
Is that per function or per section?
Per process.
Okay.
And everything's loaded relative to where the process is. Because if I run this program is actually, so this program runs with offsets right now, but GDB, for debugging purposes, always loads it in the same place anyways. So this doesn't really show much, but okay, so we can see things highlighted in red or code, right? Let me rephrase that. All of this is our program, right? And you can see it's linear. So this is 4,000, this is 5,000, this is 6,000. So the base of our program's here. If I run this the old way, that base number will always be the same, and the program is made so it uses like the same values no matter what. Now with a thing called ASLR, which we learn about later in the class, that start of the program is always randomized. And it just makes it harder to write exploits. Yeah.
But only the start, right? So the offset.
Yeah, but all the offsets are the same. So eventually what you do is So also think like libraries. If you use libc, right, your library is loaded in a random place. But the offsets of where functions are in the library is always same because you need to be able to reference them for every process. Any other questions? Yeah.
Libraries can be dynamically loaded, so how do you track down the beginning of a, or it doesn't have to be the beginning of it, but how does the process track down the location of
A separate process does it, called the dynamic linker.
And is that a hard-coded table, or would it invoke that every time it wants to?
This is things we'll learn about later in class, but if you want to dynamically load libraries, right, not your own functions, you have a table of offsets which will point to where they're in the library, and the linker will tell it when it starts running. But that's, again, this gets into like OS theory, which you kind of need to know a little bit, but not too depth. Everything, like, we just went on a tangent, which is good. That's good for the class. But we go in depth more if you're confused in like maybe a month's lectures. Right? Today we're only concerned with buffer overflows and their implications. Anything else? So this is the program that we were just looking at. Where were we? We are going to try to call a different function. So in class today, we're actually going to write an exploit script for this, right? And it'll teach you basically how to do project 2, but project 2 will be more flavored with, you have to change variables, reversing, all that stuff, right? So if you have Ret2win open, I think in one of the zip files, I gave you guys a template code. Correct me if I'm wrong, but let's start working on it. All right, so I have this code. I'm just going to get it set up so it runs template.py, okay? And then we'll load the program in GDB to actually start working on it, right? And you guys are going to make this exploit script, right? You're going to tell me what to do. So we can look at the source code real quick. Is this too small? Do you guys want me to make it bigger? Okay, I'll do one more. But what would be like a first thing we do? Consider you're just given this program. You know there's, well, we can run it. If you want to run it, we can. But you know the bug is here because you can just see gets. What's some information that we're interested in?
The address of win.
The address of when? Okay. How would we find that? Yeah.
Run it in GDB and get a look at the stack.
Okay. So we can we'll break main just so it doesn't all happen.
Can you technically break win as well, or no? Would that not really work?
We could break win,
Is if we
but
were
it'll
mid-
never get called, so GDB will never break.
Not like when it's like
the address.
Sorry.
if we were mid-exploit or something like for like future use, we want to break win to see that we actually got there.
Yeah. So if we had the actual exploit running pre-made, we could break win there, and then we could debug. Like, so one of the I'm going to leak the project a bit. One of the projects, the challenges for project 2 is jumping between multiple functions, right? So it's not just jump one function, you win. You have to jump into function 1, then 2, then 3, all in order. So what you can do is you can jump into function 1, set a breakpoint in GDB, and then you can debug your next function, and then continue to do it linearly. So yeah. Also, something to note is I broke it main here, and you see how the address is much shorter, right? And if I run VM that,
You could add a bunch of zeros, right?
oh, I have to run it. Well, yeah, but it's in generally a lower address. You see how all these addresses for our code, this is, you can see like, here's my home directory. So this is actually the file we're running and not libraries. You see how these are all loaded? That's what I was talking about, where it's consistent addresses now, right? So the code section's always loaded here. And every time I run the program, main will always be at this address. So this makes writing our exploit possible, right? Because if not, every time we ran the program, win would be at a different address that we didn't know. But now we can hard code it. And, you know, really, in real life, it's not really at that address, but we can use that address and the operating system does all the virtualization for us, right? So in practice, we can think of it as that. Any questions on this? Okay, so where were we? How do we get the address of win? What's the command? Yes.
Is it X star win?
That might work. Yes, it did in fact. Or is that correct? Yeah, okay, sorry, it's this one. X examines the data, so this is probably actually the code of win, and that's why I was confused, but the pointer, which is win, and remember that this is actually a symbol, so I could compile this program and strip the symbols so you don't have like debugging privileges, and we wouldn't be able to do this. But because we have symbols, the pointer to win is kept in memory, okay? So yeah, we have win, this is the address, right? So let's put this here, right? So what is it, 401156. What's the next thing we want to do?
Start the execution till like we reach the gets thing.
Okay, so we want to get to gets. So let's disassemble main. Where should I break? At the call?
Yeah.
Okay. And we'll run it. And I'm broken at the call. What do you want to see? We can see the function, previous functions, if we were interested in, changing the stack for libc start call. In practice, not very useful. We can see the current stack. That might be interesting. The disassemble, which, let me continue again so we actually we're at the call now. You can see we're broke here. Debug is also useful because it'll show you the arguments if we step into the call. And then the registers. What do we want? What are we interested in here? Keep in mind the source code, right? The source code tells you how big the buffer is. The compiler may make it different though.
I was going to say the size of the buffer.
Okay, so what we can see just from being in main and using Debug is RSP's here, RBP's here. So the entire stack is this length, which looks to be 0x 20 bytes, right? Okay, so what does that tell us? Yeah.
Anything after that, after those 20 or after those 32 bytes, will basically overwrite those addresses.
Yeah. So right, if we do 32 bytes, the start will be right here.
Could we because they're the same process? Could we compute the difference between those two addresses? Write that length minus 1 to get to that address.
Okay. Repeat.
So we have the address in main, right?
Yes.
Keep going down to get to the address, which is the address of the win function.
Yep.
Could we just write actually, can we get the address of the return address as well?
Return address is always right after base pointer.
Yeah,
so this is the base pointer.
Yeah.
This is the return address.
So
and real quick, you can also see Debug because it realizes after the base pointer is always the return address. It shows that the value here is where you return, right? This thing in red is code. So this address, it'll also tell you libc start call main, so it tells you where we jump into the previous function. So it's just a little thing you can see where it's supposed to return. So you're asking if, because main and win are close, if we only change that last byte of the return address, like instead of overwriting the whole thing, we can only overwrite one byte?
Yeah.
Yes, that is useful in practice.
That is how, for example, if you only have 1 byte out of balance, you might be able to use that for something like that, for example.
Okay.
Good. Where are we in our exploit? What do we want to do next?
So we have pillar for 32 bytes, where whatever.
Let's raise hands.
Bytes, and then add the memory address, which is do a 0x4.
Okay. Yeah, but let's raise hands. So we figured out the stack of things that we can just overwrite, not useful. It's 32 bytes. So let's add 32 bytes to our payload. I'll eventually send this, but we're just making the payload for now. What's the next thing we want?
A little side note. Shouldn't it be Ret2win instead of template.py at the top?
Yeah, you're right. You haven't ran it yet, so. I love doing scripts live. Okay. Thank you.
And then add the win address as a binary.
Not yet. Okay, so we filled the stack. What's next? Yeah.
Do we want to give it the return address?
Return address, but there's something between the stack and the return address.
Build a RVP.
Okay, RVP. And this is probably a good place to check to see we're doing the right thing, right? Because if this isn't working, then nothing's gonna work. So we're just gonna write something to send the payload. The interactive line just means that once a Python script does all it sends and reads, we'll actually just get access to the program like normal. And in the GDB script, I'll just do a break at main so we can actually see it in a debugger. Okay, how do I want to do this?
You have a.
Is that supposed to be
There's three dots.
Where?
Interactive.
That's my VM lagging if I type things multiple times.
Do you have to do P dot, like the P.io?
Oh yeah, let me say that. We'll see. Does this work? Probably not, but we'll see. Okay, so the program, because we attached GDB, runs. For some reason, break main didn't break, but we'll continue. So let's just disassemble main and break after the call just to see if things are working. Continue. Okay, so we did the call, and let me make it bigger. Let's actually look at the stack. So, right, what we can see now is the value that RVP points to is actually all Bs, right? So if we examine RVP, that is the value of all Bs. Interesting, right? Is this? Okay, examine just does 4 bytes, but it should be 8. Yeah.
So we need to do another 8 to get to
Yeah, but now we can see we're overwriting the correct amount for the stack.
Okay.
Right? So even though the buffer is only 32 bytes, we need input 40 to actually get to the return address.
Yeah.
Right? And then for the previous function that we were looking at the beginning of the class, because of the compiler being weird, we'd have to do extra bytes. So it's always good to run things in piecewise and check your exploit working along the way instead of trying to do it all in one shot and then spending an hour debugging. Okay, so let's quit this.
Are we supposed to do P.io before we do P.interactive?
It worked. I don't write this
I don't
scripts.
think so.
I don't think
I'm
so.
not sure what p.io is.
It was there in the GDB cheat.
I'm not sure. I've never used that.
Also, what's the other command besides GDB attach?
.debug.
Okay, yeah, we should use. You guys should use debug. This is an issue that we ran into last year, and that we're currently experiencing. So attach. This is like a finicky thing. Attach runs the program, and then attach GDB to it. So the reason we didn't break at main was because the program started running for a bit before the GDB process started and attached to it. So we missed the breakpoint actually in execution. But if you use debug, it'll launch GDB and then launch the process. So if you spend an hour going crazy on that, that's why. We had multiple kids do that last year before we found out. But I'm not going to fix it now. So let's go back to our payload, right? So we know that we're at the return address, right? So the next 8 bytes should be what? Yeah, the win address, right? So we have the win address here. Something that you're going to want to make use of is the P64 command. This stands for pack64. It takes an integer and writes it in the corresponding bytes in little endianness, because that's how computers want to read it in, and it's really annoying. Else you would have to do 0x56, 0x11, and then you have to do it in reverse order. And then if you have issues like if it's 32 bits or 64 bits, P64 does that all for you and makes your script look really nice. And you just put WinAdder as a parameter, right?
So it accepts even X values. You said it.
Well, I set WinAdder to a hexadecimal number, but it's just an integer, right? I just writing it into hex. Any questions on that? Yeah.
I'm getting an issue that says could not find terminal binary VS Code when I try to run it in VS Code. Is there a quick fix for that?
That sounds like a VS Code issue and not my file. Hopefully. I don't think I have VS Code in this. Anything else? Yep.
Is anyone else able to get the file to run in GDB without having to compile it as a different thing?
Yeah, I didn't compile it with it. I have to, every time I need to compile it for someone that runs an older OS, I have to spawn a Docker container have it compile in the Docker container, take it out. So my bad. The project will be fixed, I swear, but not fixed. Yeah.
Is the B times 8 there because the RBP on the stack takes up 8 bytes?
The B stands for write this as bytes.
And
And
no, I meant like because you're multiplying by 8. Is that because?
oh yeah, sorry. This is just me doing Pythonic things. So if I do times 8, it'll do 8 of that character.
Okay.
Right? And if I think if I do it as a longer string, it'll do 8 that string. And then I just do it as bytes because Pwn tools will yell at you and sometimes have it'll do wrong things if you give it ASCII and not bytes.
Okay.
Even though it technically is the same thing. You'll be surprised though. There's a lot of edge cases, right? Because if we're doing this in Windows, again, I shit on Windows all the time, but Windows has multiple versions of characters for backwards compatibility. It has ASCII, so like every Windows function, like quite literally every Windows API function that takes a string has 2 versions, one for Unicode and one for ASCII, and one's 16-bit, one's 8-bit, and you can never tell the difference if you're like reading any file type. So you just have to guess, check, hope, right? And things like this fix it. So that's why I use bytes. Because then, like, if you were to do string, Pwn tools would then call like dot encode with a random 1 that you might not want.
So does that make like Windows?
Yeah. This just makes Windows objectively more annoying to code. It's just so much of Windows is just really bad backwards compatibility. Like, okay, the current operating system still runs MS-DOS in the background, and then calls MS-DOS APIs. Yeah.
Emulated because it's funny.
Yeah, it's all emulated, but at some point it'll still run MS-DOS.
It's emulated.
You kind of went over this already, I think, but I think I missed it. So when you're multiplying by 32 for the A's, how did you make sure that the buffer is 32? In the source code it says.
Yeah, no, that's a good question. So we just saw here that, right, so there's multiple ways you can do this, right? The first way to do this, which is probably, okay, if my VM wants to work, give me a second. We could disassemble main, right, and actually look at the assembly. And what we see from this is that we subtract 32 bits from RSP, right? So that tells us all the local variables use 32 bytes, okay? And then if we want to further investigate the buffer we're using, we can see that in our gets call, we're setting RAX to -20. So the first parameter for gets is the location of your buffer. So we can first see how big our stack is, and then where in the stack our buffer starts, okay? And that might be different because of things like changing the order to protect parameters, okay? The naive but efficient and very used way is just to run it and see where it is, and then just break and say, oh, that's where my A's went, okay? Yeah.
So couldn't you also just even without exploiting the buffer, couldn't you just look at the difference in the this? I think this would have the word last.
So you can see.
You just look at the difference, and you realize 32 bytes, and you just write. If you want to write.
Yeah, so that's what I was saying. Like you're subtracting, and then in Pwn Debug, running it live, Pwn Debug shows you where RSP and RBP is, right? Which is convenient in this case. But then, like, say your program pushes and pops things to the stack, right? And that's not consistent. And then maybe your buffer isn't at the end of the stack, so that wouldn't tell you exactly.
Okay.
I mean, in real life, I'm very, I want to say efficient, but it's just me being lazy, and I'll just type A's and then look at the stack and then say oh, it's roughly this, and then keep going until I overwrite the base pointer and be like, well, I basically just binary search it, and then because one thing you can do, which probably people will do on the project, is I'll just go hold the A key until it crashes, and then I'll just delete one A until it stops crashing, and then I'm at the return address, right? Okay. Anything else?
Would that be the end of the return address? So you have to.
Yeah. So if any of the
there are better ways.
There are better ways to do it, but that's how I consistently do it.
We'll talk about a better way later.
Yeah. If any of the return address is corrupted, you're most likely going to crash. There are very rare scenarios where it's conveniently not crashing, which will piss you off. But most likely you will crash.
So once you get the correct data, you're at the start of the return.
Yes. And anything else will corrupt it. And you may still crash regardless because you're corrupting the base pointer. And then your stack is corrupted. So really, who knows? Yeah.
This is probably like a dumb question, but instead of calling the function that's like if you wanted to call your own function, how would you do that?
You talk about that later.
Oh, okay.
So literally next lecture, we say, hey, calling the actual functions is boring. Let's put our own code in there and then write malware. And that's next lecture. So yeah. Okay, anything else? Or should we run our exploit and see if it works? Yeah.
So that on line 3 of the script that you wrote, is that Judy script to break main or is that just break?
Yeah, I'm breaking at main, and then I was complaining earlier, it didn't actually break at main because I'm doing attach and not debug.
But is it the same? Is it the same function?
It runs the command break main, but it attaches too late.
Oh.
So it's being really annoying. Anything else? Okay, so let's actually run it. And hopefully, if I can code right, it'll work. And like, just for your reference, like, what this script looks like roughly is exactly, like, the projects are a little bit more involved, but roughly this is like all you need to do for the projects. And roughly this is all you need to do to write real exploits once you find bugs in like real world. Like you'll be very surprised how easy it is to write exploits. Finding bugs is the hard part. Okay?
Sounds like a target.
Yeah. Mr. Google Chrome. Yeah. Okay. I don't care about this. Right? It printed you win. Isn't that exciting? If you caught it for like one frame, it conveniently also segfaulted, which is something that, maybe you don't want the program to segfault after calling the first function that you want to use. But our payload did correctly overwrite the return address and call an unintended function. Cool for this class, but think of the implications. There's so many bugs. I'm a Windows guy, so there's so many bugs in like random Windows drivers that have things exactly like this, where you can then start calling any functionality in the kernel. Or like, what's other things? There's bugs in everything. I just want to say that. Nothing's secure. Yeah.
Did it segfault because like we switched off the base pointer, or was it because we haven't given another return address?
Okay, so think of two different things, right? One, did we provide it? So we didn't properly use the call opcode, right? So we never pushed a new return address for it to get, right? So think of, one, we never called win properly. So there's no return address, there's no base pointer to return to. Two, we corrupted the base pointer in our exploit. So the stack on the new function, when we call win, is just complete garbage. So it could have segfaulted for multiple reasons. Stuff you can do is, in your buffer overflow, some of the data you're writing, if you can get the correct leaks to like where the stack is, you can write a new stack and then set that for the function you're calling. And then hopefully you can like make it exit gracefully. But in reality, it's a little harder sometimes.
Wait, could you just show how you got the win's address again? Sorry.
I just did probably disassemble win is an easy way to do it. Or you could examine win as a pointer. Win, because I didn't strip it, is actually a valid pointer in the list of symbols we have, right? Also, if you open it in Ghidra, because this is compiled to run at the same location every time, this offset is in Ghidra, where the actual function starts in the programming Ghidra on the decompilation window is the same one that it's being used here. Yeah.
You said that once you get the buffer forward, you can call any kernel system call. Can you? For
some programs, right? That's not going to happen with a normal user application. But if you find bugs in Windows drivers, then you are running it at kernel level. Yeah.
Wait, so you can make system calls if you do it right? Wait, what did he say? I didn't hear.
If you find bugs in a kernel level process,
Oh, okay.
you can then call any kernel function,
Okay.
and you'll have kernel permissions, which means you bypass things like memory checks, right? And you bypass all protections because I don't know how Linux does it, but at least in Windows, every Windows function, even at the kernel level, checks if you have kernel permissions, right? And it'll check if things are inbound. But if you have kernel permissions and you exploit a program running in the kernel, then you can literally do anything. Like, it just ignores every check because it just assumes it's correct.
And hypervisors come in.
Yeah, and then you try to break out different things. Yeah.
If you have gets, what's like stopping you from printing out or calling like print to print out where you are, like printing out a pointer where you are? Okay.
Nothing later.
You can do that.
In like a week. Okay. Any other questions? I think we mostly covered what's on the slides. You can do things anywhere in program. You can do this on your own time. That's the last slide. Okay. Yep. Any other questions? Else we're going to talk about the final presentation for the class. We're going to get started. Okay. So this is the week that we want people to start thinking of presentation ideas, right? You got your hands on what reversing is as a topic. You now dip your toes in the first exploit. We don't expect you to, come out of this class finding 0 days in applications, but we want you to do independent research, right? That's the goal. So ideally by Gilbert Tuesday, right? We want you to either find people you want to work with, right?
Not yet. Just like right.
Well, like, if you have people you want to work with, we'll make the groups. But if you have like a list of people you want to work with, we'll keep that in mind in like the survey we hand out. But the more important thing is like start thinking of ideas that you want to do, right? So the goal of the presentation is for you to find something that some people use, right? It doesn't have to be a lot of people. It can be a few hundred maybe. But we want you to do the process of reversing it, to figure out how it works, right? With the idea of looking for bugs. Maybe if you're doing a certain type of program, you'll look up bugs that aren't in this class, right? If it's not just C code. But we want you to really like start the process of trying to be a vulnerability researcher. So good projects that we've seen in the past have been someone was a Game Boy, knew how the Game Boy worked, and wanted to see if they could figure out how the Pokemon trading worked on Game Boys and see if they could corrupt and exploit Pokemon trades, right? So you could like either steal Pokemon or it would appear that you're making a trade with the Pokemon you want, but then when the actual trade happens, you get something else, right? And that was like them reversing the hardware, finding space for payloads in the actual ROM of the game. That was a great project. We've had other people dump firmware routers, figure out how routers work, and try to look for bugs in the processing of packets. Someone talked about us doing it for this semester, patching a bug in an emulator that doesn't let one of your favorite games run, right? Things like that. Like you can come up to a bunch of, there's a bunch of different things you can look at. And if you are having trouble, you can ask for us. But you can do different hardware things. You can do CPU bugs. If you want to look at the Linux kernel or Windows kernel, that's a huge task, but it's super interesting. And we can help you with that. If you have an idea in mind, you can talk to us about it, and we'll say if it's a good idea or not.
If you have some random, let's say maybe a PDF parser you like to use that's not your browser, that's something that's like maybe not a lot of people use, but you like to use it for some of its features or whatever. Maybe that could be a good target for you. Look into how the PDF parser works and see if you can find bugs in that and stuff like that. Later in the course, we're also going to be teaching you some automated program analysis techniques. So for this project, you're first choosing a target with your group, and two, kind of getting an understanding of how it works, getting familiar with their code base, kind of mapping everything out, and then both looking for bugs manually and also instrumenting it with one of those automated techniques.
And I guess I didn't say this. Ideally, I don't know how many kids we still have in the class, but groups of 3 or 4 working together. And the end product is probably going to be a 15-minute presentation where you explain some technical details to us in the class about what you're reversing, how it works, If you found anything that looks like a bug or any ideas of, maybe we didn't find a bug, but this seems like it could be vulnerable and more research needs to be done. And then probably like throughout the semester and at the end, like a complete list of like documentation of your reversing. So like we have proof you're actually doing the project. And I want to say that like the people that really put effort into it come out like loving it. Like it should be like a lot of people have fun with this. It looks great on a resume. Like Jesus, like the people that did Game Boy hacking, instantly a job at like a contractor doing the same type of work. Like right, it puts you miles ahead of any other student at other schools. So I really hope people care about the project. That being said, questions. I know we were kind of vague on it, but we want you to start thinking about potential ideas.
I think we're releasing a quiz today, you said, right?
Yeah.
On the quiz, we'll add a question where you just maybe list down like 3 topics that you might be interested in working on, or like 3 targets, things you might want to explore. Yeah. It doesn't set you in stone for that yet, but just to like think about it a bit, get some ideas down.
I mean, just some more examples. Maybe we rephrase them a little bit, but people like last year took the exploits we did in this class and then tried to repurpose them on Windows, right, for Windows programs. Some people did like meltdown inspector CPU bugs. If you want to do something like that, maybe you write like a little CPU emulator and you try to emulate the same type of issue.
Is anyone here in CS 535?
Lucky.
Okay.
Yeah. But like that's some stuff you can be into. Any questions for the presentation?
You target like embedded systems.
Yeah, if you want to do hardware, that's great. The club has all the, or most.
Yeah, we have some equipment in the club, stuff like soldering stations, flash programmers, basically stuff where you can take off chips from devices and read them into your computer, and then you can load the firmware into Ghidra and start reverse engineering. A team actually tried that last semester as well, and that was a pretty cool project.
Yeah.
So if that's something you want to do, we definitely encourage it. It's on the harder side, so you got to be ready to put in some effort, because especially if you're dealing with hardware and you may not be super experienced with it, stuff can go wrong. But it's a really interesting project.
And going off that, like, definitely don't be afraid to do something hard. That team, like, killed 3 routers, right? Did they even dump the firmware at the end?
I think so.
I don't know, but like now they're like doing all like they're hacking printers now, right? And as long as you like show us like legitimate like effort throughout the semester, even if you fail miserably, you'll still be fine. Like right, this is not like I need a 0 day that we can report to the company or the government by the end of the semester. This is like try your best, okay? If you don't show us consistent results, then we'll be like, oh well. But if you say, hey, I tried this and failed 5 times, that's great, right? That's how everyone gets into this field.
Did you have people do kernel stuff like in the past?
We had people learn how to do a kernel, but no one like tried reverse engineering it. If you want to do kernel stuff, I can toss projects I've done in the past, and that'd probably be a great way into it.
We had one team that very lightly touched an Android kernel exploit, but they didn't go very far with it.
I should say things that we don't want you to do.
Yeah.
What we don't want you to do is find a blog post and then copy and paste the blog post. If you say, hey, I want to do Android app hacking, and I find a blog post on an app and this specific type of bug, and I just show that I can do it too, that is not original research. What you can do is find an app I want to look at, say, hey, this app uses the same library as this other app that has issues, see if I can port it over. That's great, right? That's how real world research works. But try not to do the exact same thing. We will know. Anything else? Yeah.
Sorry, I wanted to add. I'm really interested in devices like AirTags that are put on people and can be used to stalk other people. So if you can show that you can take a Tile device or Apple AirTag and disable the security functions, and then we can report that to Apple and the world, by the way, like not so that you can use it for something. That would be great. And same thing. If you get nowhere, fine. But that you could think of that as an alternative to, this class is not just about getting access to the file system, right? So that you can do something. It's to turn off or disable things that maybe shouldn't be able to be turned off, right? Things like that.
Yeah.
For other reasons.
Can I talk about the Echo Dots?
Yeah.
Yeah. So like one of the projects we're doing right now is, say you're unfortunately, like your ex-spouse comes and murders you, right? Yeah. But say that happens, if their phone connects to a Bluetooth device because they used to live there, can we get Bluetooth IDs off the device and pin people to say like they were here at that time, right? And just information disclosures like that have like very like large effects on like law implications, and like like things like that, which aren't just strict bugs, but like information disclosures, also super important. Those get reported all the time. So figuring out how the system works and seeing what you can get from it, even if it doesn't lead to code execution, huge, right? Imagine if I can ping any network and get all the users on it, right? Google would pay me thousands of dollars for that. Things like that. Or like, I guess Windows in this case for Active Directory, but also important. Exploit development actually probably is going to be the smallest part of your project. I would be surprised if anyone here got a working exploit. Yes. If you do, I will get you a job. Okay. Any other questions? Yeah.
Working exploit in what specifically?
I know you're fishing for blockchain stuff. Come on. You're not even enrolled in the class. Okay. What else? If no one else has questions, class is over in a minute. You can come up to us if you want to